హలో, వినిపిస్తుందా? హలో, మెసేజ్ చేయ వాట్సాప్లో. ఓకే. ఓకే, వెల్కమ్ టు క్లాస్ వన్. క్లాస్ వన్. ఓకే ఓకే ఓకే. Okay, let's talk about the thermodynamics. What is meant by thermodynamics? A branch which deals with heat, work, and temperature, and their relationship. Relationship to energy, physical properties of matter. A branch which deals upon the heat, work, temperature, respectively. Basically, JE and NEET, both syllabus same. You can follow this lecture too. Coming to the ideal gas equation, what is meant by ideal gas or real gas? Here, there is no force of attraction. Here we can see intermolecular forces. Okay. What is ideal gas equation? PV is equals to nRT, which gives a relationship for both temperature and pressure. Let us do a problem which is related to the JE. Okay. Initially a gas. Okay. Let us solve afterwards. Let's move on to the new topic. What is degree of freedom? Do someone know about this? Let me tell you about this. The number of ways or modes in which a molecule, let me erase it. Okay, let give me some time, I will fix this. The number of ways or more in which a molecule can acquire kinetic energy, I mean internal energy, is known as degree of freedom. Basically, degree of freedom is of four types: monoatomic, diatomic, polyatomic, in linear. Poly, non-linear. Okay. Okay. Let's talk about the monoatomic. Monoatomic gas. Let me give me a color. Let me take a gas of a single molecule with a nucleus which have a translation motion of x-axis, sorry, y-axis, x-axis, and z-axis. What is meant by a monoatomic gas? Let me tell with the example. The examples of monoatomic gas are helium, argon, any noble gases. Monoatom, which have single molecules. The translation modes of monoatomic gases is three. I mean, of mvx square, of mvy square, of mvz square. Yes, this all. Sorry for the voice break. Okay. Let us talk about the degree of freedom of monoatomic gas is 3. Okay, let me give me with a new color. The degree of freedom of monoatomic gas is 3. Okay, let me change the color. Okay. Coming to the diatomic gas. Diatomic gas, basically, the examples of diatomic gases are oxygen, hydrogen, nitrogen. Uh, O2, O2, H2, N. The examples. Let me take an two diatomic molecules with a nucleus which have y-axis, which has x-axis, which has z-axis. We all know that kinetic energy of y-axis is of I y omega square. Since moment of inertia we have learned in our previous class. The moment of inertia is of I omega square for a rotational modes. Coming to the derivation, kinetic energy of y-axis is of omega square into Iy. Okay, let us take an example of diatomic molecules which have a nucleus y-axis, x-axis and z-axis. The full atom mass lies in the nucleus. We all know that. In an atom, 99.9999 percentage fill its space. Only that not 1% will be filled. Okay. Point mass of a nucleus is mr square. Okay, one atom is mr square. మాట్లాడుతారు రే ఏంటది and the atom nucleus mr square. If devil is ഒട്ടതാണ് ക്ലാസ്. Substituting the I y I j. अरे देंगे एक नीचे थोड़ा. ओके कन्वर्ट कर रहा है. 2 minutes. Okay. Let us continue. Sorry. Kinetic energy of yx. Okay, it's not visible. I will continue with another color, darkest color. Okay. Kinetic energy of an y-axis is of I y omega square is of 2m r square into omega square. mr square plus mr square 2. Okay, let me not derive with this. Let me erase this. Okay, kinetic energy of z-axis similar to this of Ij omega square is equals to of 2mr square into omega square. But kinetic energy of x-axis is 0 since the reason is a atom which nucleus lies in the axis of x-axis. We all know that. Okay, I mean, do you understand? Always nucleus here, here nucleus lies on the x-axis. Therefore, Ix is equals to 0 of Ix into omega square, which tends to okay, let me erase this. Tends to 0, which gives me 0. Okay, let me give me another color. Okay, therefore the translation modes, the rotational modes, the translation modes are 3: Vx, Vy, Vj. The rotational modes are only 2. Here we can't move in this case. Okay, the rotational modes are 2. Here we will introduce another one, vibrational modes. Do it vibrational modes. Vibrational modes in diatomic gas. There are two conditions. One is at high temperature, and there is at ordinary or normal temperature. Okay, let us take in diatomic molecules. Okay. Okay. Let me give me another color which you can be easily visualized. Okay, let me take in two diatomic molecules which have a nucleus only. Let us take an hypothetical spring in this between molecules. Here we have an dun, dun, dun. Okay, sorry for the inconvenience cause. With these two diatomic molecules which have of kx square plus of mv square, like kinetic energy and potential energy. These two energies can exchange like this. We can say this. At high temperature there are two sorry. At high temperature we have two modes, and at ordinary we have 0. Therefore, let me give me with an another. Therefore, F diatomic at ordinary temperature, at high temperature is 5, and we get 7 here. Okay, let us go to the other one which deals. Okay, let me take this color. Okay, and add in thickness like this. Let me go polyatomic linear. Example C1. Let me take in colors. Sorry for the inconvenience causing. Okay. Taking example like CO2, let me give an example visualization. which is a diatomic molecule. Cargo. That means take an polyatomic linear which having a nucleus Vy x of V axis and Z axis. There are the translation modes. Translation modes are three, and rotational modes are two. Let me go to the polyatomic non-linear gas. The example of polyatomic gas is, let us take CH4, ammonia, and water molecule, and so on. Let us take in polyatomic non-linear gas molecule, which is like in this. Sorry for the diagrams. Y axis, x axis, and z axis. Okay. Let us take the translation modes 3, the rotational modes also 3. Since here we have 2, the reason we all know that nucleus, here we can move, but here the Ix is equals to 0. Here it was far away from the nucleus, we can rotate it here. Therefore Ix is not equals to 0. Therefore degree of freedom of polyatomic is 5 for linear and 7 for non-linear. Okay, let us go to the law of equipartition energy. Sorry, a small calculation mistake here. The polyatomic non-linear molecule is 7. No, I was calculated wrong. 6. Okay. Okay, I'm ready. Start చేస్తున్నా. Bye. Okay, coming to the law of party equipartition. The law of equipartition states that the average kinetic energy of each molecule per degree of freedom is equal and same to of Kate. Sorry, Boltzmann. Okay, we all know that KB is known as Boltzmann constant. KB equals to R upon Na. R is universal gas constant and Na. హలో వినపడుతుంది కనబడుతుంది ఇప్పుడు కనబడుతుందా చూడు రాస్తుంది ఓకే కట్ చేసినా ద the average kinetic energy of each molecule per degree of freedom is same and equal to of Kt. We know that Kb is equals to Boltzmann constant. Kb is equals to R upon Na. R is universal gas constant. Na Avogadro number. Okay. T is absolute temperature. That is the average kinetic energy per degree of freedom is equals to of kBT as we discussed here. Okay, let me give me with another color. Let us take blue. Average kinetic energy per molecule yet degree of freedom is equals to of kT over 2. The total kinetic energy of n molecule, simply keeping n in the above equation, gives us the total kinetic energy of n molecule. Okay, let us discuss about total number of kinetic energy of 1 mole gas is how much? Let us tell us I will elaborate neatly. Kindly concentrate here. We all know that kinetic energy sorry I will erase. U equals to Na into K F T by 2. We know that the Boltzmann constant Kb equals to R upon Na, as we discussed here too. Okay. Okay. Then I can write Na into K like R. Since Kv into Na gives R. Since therefore R into F into T by 2 gives me the total kinetic energy of 1 mole of gas. Okay, let me give me with another color. Total kinetic energy of N moles. Very importantly, U equals to NFRT over 2. Very important formula. Okay, since internal energy increases, temperature also increases. As we know that and landing states of matter, Vrms equals to root over 3RT by 2. Since Vrms increases, here T also increases. Very important. Okay, let us go to the table itself. Let me take an okay, let me take a time to understand very deeply to this chapter. Since 2 to 1 question will be given in the J and 1 and 2 to 3 questions in NEET. Let me give to this gas. Degree of freedom and internal energy, molar specific heat at constant pressure, at constant volume, and gamma. Degree of freedom, translation plus rotational plus vibrational plus U. We know that NFRT over 2. Okay, let me give me this here. Internal energy and CV molar heat capacity of at constant volume at constant pressure and okay, let me allocate it very elaborately. Okay, monoatomic, diatomic, polyatomic, linear, polyatomic, non-linear. We know that degree of freedom of monoatomic gases is 3 plus 0 is 3. For the diatomic molecules we have 2. At normal we get 5. At high temperature we get 7. For the polyatomic molecules 5. 3 rotational, 2 rotational and 3 translation. Here 3 rotational plus 3 translation plus 3 rotational gives rise to, we give 6 degree of freedom. We know that U equals to NFRT over 2. Substituting F in the values of degree of freedom, we get 3 NRT over 2 5 NRT by 2. Okay, let me erase it. Seven NRT by 2 and 5 NRT by 2. I am not doing anything here. I am just applying this here in the F place, and 6 NRT over 2. We will discuss these three after molar heat capacity when we discuss about the calorimeter. Okay, let us go to the internal energy. The name itself tells about this. Thermodynamics is nothing but the day-to-day life. From the internal energy is nothing but sum of all energies, which gives us internal energy is equals to kinetic energy plus potential energy. Ke plus P. Ke is NFRT over 2. Potential energy is 0. The reason behind this is the simplest reason. There's no intermolecular forces of attraction between the molecules. Simple. Therefore, internal energy is equals to NFRT by 2. Okay. The total internal of gas depends upon temperature only. It's independent of pressure and volume. Therefore, change in internal energy is NFR delta T over 2. Many times it was asked in JEE. Okay, this is the basic idea of thermal equilibrium, internal energy. Let us go to the thermodynamic state. Let me give me another color which suits. There is nothing but okay, very light. Let me choose a darkest color. Okay. Thermodynamic variables. What are the thermodynamic variables? Let us discuss. Pressure, volume, and temperature. Which this denotes the thermodynamic variables. Pressure, volume, temperature. These are variables collectively represent thermodynamic state of any gas. What is meant by thermodynamic state? First, understand about what is meant by thermodynamic variables. The collection of thermodynamic variables is known as thermodynamic state. Okay. Let us go to the other one. Okay, let me choose this color. Okay, coming to the state function and path function. Let us give us an example. What is meant by distance? What is meant by displacement? Let us know about this first. Going on to the state and path. Let us take in 2 points A and a B. Let us give a path like this, and there's something this path to reach B. Okay, let me choose another color to the best visualization. The distance is called, the distance is path difference. The displacement is path independent. Distance is path dependent. Displacement is path independent. It can be this or it can be this to reach ultimately the B. Okay, let me erase this. Coming to the state function, the thermodynamic parameter which only depend on initial and final thermodynamic state.
హలో
చెప్పు, ఇప్పుడు కనబడుతుందా? చెప్పు ఇప్పుడు. ఓకే, ఓకే కనబడుతుందా? ఓకేనా? ఓకే. ది thermodynamic parameter which only depends on initial and final thermodynamic state. And clear, I am telling clearly, not on the thermodynamic process. The thermodynamic state, as I clearly told the before slide. Let me recall it. The collection of or collectivity of these variables like pressure, volume, temperature. Okay, the example of state function is simply internal energy. Let us go to the path function. What is meant by path function? The thermodynamic parameter which depends on thermodynamic process along with the initial and final state. Example, let us take simply the work done by the gas. We can clearly understand on the next. Okay, let me erase this on the next slides. Okay, work done by the gas. Let me take in container. I will place a piston above piston which is a movable. I will place a piston which is movable. I will take in gas molecules. I'm taking randomly, since there is no distribution in, it was not tightly binded like solids. Gases are lightly, sorry, gases are tightly, sorry. చెప్పురా బా ఏటి కనబడుతుంది నీకు ఇప్పుడు? పైన ఏటి కనబడుతుంది? పిస్టన్ అవన్నీ రాశాను. ఇప్పుడు నీదిరా, నేను చూడక్కర్లేదా? ఇప్పుడు మళ్ళీ రాస్తానుండు. Okay, let us take hand container and then piston in that, which is a movable. Let us take in gas molecules. We know that gas molecules loosely bind solid tightly bind. There is no uniformity in this distribution. Okay, let us take this. Due to some, okay, let me give this with another color. Let us give it with pressure. It will move from the initial pressure to the final. Let us take this as V initial. It was taken as V final. The a small, I will consider a small element dx. Okay, the force applied by gas on piston. I mean, I'm telling this. We know that force equals to pressure into area. F equals to P into A. Let me take work done by the gas. W equals to integration of F into dx. F equals to PA into dx. Let me consider A. Let me take another color. Okay. This area as D, a small element of volume. Okay. Therefore, work done by the gas is W equals to V initial to V final P TV. Okay, most important form. Let us learn deeply in this slide. Okay, consider a graph in PV graph. Okay, let me take this pressure and volume this side. Let me take somewhat. We know that area is equals to P into dV is equals to work. Area under PV curve gives magnitude of work done by the gas. Simple. ఈ ఈ ఏరియా ఉందా, ఈ ఏరియా దీని వర్క్ డన్. ఈ వీళ్ళ ఏరియా అండర్ కర్వ్స్లో మనం నేర్చుకుని ఉంటాం. ఈ I will tell more here. Let me take one. ఈ అక్కడ మనకి ఎంతైతే ఏరియా ఉందో ఈ ఏరియా యొక్క పీవీ కర్వ్ ఉందా, ఎంతైతే ఏరియా ఉందో అదే వర్క్. మనం మ్యాథమెటిక్స్లో ఏరియా అండర్ కర్వ్స్లో తెలుసుకుంటాం. సింపుల్. ఓకే, there is a doubt. What if gas expands and compressed? Or take a value. Example. Expands, compressed. Let me give an neat visualization like a PV graph. Let me take an volume of V initial and V final. Okay, this color was not visible. Let me take an color which can be visible here. Let me take an color red. I am taking an area of this. Since the work done is in from here initial to final, then work done is positive. Since Vf is greater than Vi, it's a positive graph. Let me take, since here I will take like in case 1. Here the gas was expanding. Let me take in case 2. Here the gas was compressing. P V. Let me take in V final here and V initial here. The direction like this here. Then the work done is negative since Vf is less than Vi. Okay, work done by a cyclic process. Let me take two graphs. Let me take in graph like Let us take pressure and volume. V initial, or let me take an end round cycle. Let us take an cyclic process because the name itself tells us a process. Let me take an cyclic process A, B, C, and D. Let us take the work done like this. Like let us take two work done here to understand this. Work done total is equals to work done W of ABC minus work done of CDA from CDA and ABC. Here we get two results. Let me take with another color. Let us take green. P and P. Let us take in circle of A to ABC like this. Here it's okay. From here the work done of ABC, the work done of CDA is like okay. Let me take another color to understand clearly. It's an cyclic process, clockwise cycle, anti-clockwise cycle. Here work done of ABC is positive, work done of CDA is negative. Therefore, work done of total cycle gives us the what? Area under the circle. Here gives us the results. Let us do a problem from the above. Let us solve together. For a given cyclic process, for a given cyclic process CAB as shown, It's an cyclic process. Anti-clock or clockwise. First, determine. It's an clockwise direction. Let us take an graph, an empty slide. Let me take an black. Here we all know that work done of the cycle process gives by the area. Here area of a triangle of BH square. B 4 meter cube. H, okay, 5 pascals is the height. And the breadth from the figure here the height is sorry the height is 5 pascals and the length is 4 meter cube. From the figure we can show breadth is 4 pascals. Therefore height is 5 pascals. Substituting by we get the work done of into 4 meter cube into 5 pascals. Pascals gives raised newtons per meter square. Newton per meter square. Meter square and 1 meter square cancel, and here we will have to buy the 1 meter and these two cancel, and we get 10 joules. We know that it was in the clockwise direction and gives its positive sign 10 joules or 10 newton. Okay, like this we can solve this question. And joules is answer. Okay, first understand, second graph, third sign, fourth applying formula, fifth required answer plus 4. Okay, let us come to the zeroth. Let me take body B and body C. Let me take A and B contact with C. Here A contacted with B, A, B, C. Let me take with another. If A, B are in thermal equilibrium and B and C are thermal equilibrium, then we can say that A and C will also in thermal equilibrium. Like this. Let us consider a body B and body B and body C like this. We can say this. When A and B are come closest to the contact, A and B and C are in thermal equilibrium, then we can say that A and C are also in thermal equilibrium. Okay, let me clear here. It will also useful in our boards. I have forgotten to say that here zeroth law tells about the principle of temperature. Therefore, TA is equals to TB is equals to TC. Let us take an enclosed vessel with an internal energy of UA and a small closed vessel UB. Let me take another color. Okay. We also see in violet filled with the containers in B. Therefore, we can say zeroth law. Ice at 0 degree Kelvin. Since energy transfer, energy flow from higher to lower, therefore here UA is less than UB and temperature of TA is less than temperature of B. Let us take an container. Let us take in gas molecules. I will color it with violet. Let me take an measurement of temperature with thermometer. The amount of heat we get, the change in heat, and we get here the work done. Since the first law of thermodynamics states that the principle
Off.
law of conservation of energy. Let me take another one here. Energy neither created nor destroyed. But in but this also stated but in isolated system the sum of all forms of energy constant. Okay, therefore del q equals to amount of internal energy and change in work done. We know that del q equals to heat supplied to the system, work done by the system. Here, coming to the science convention, heat is supplied to the system is del Q gives us positive sign. Heat is extracted from system gives del Q is negative. Del Q coming out is negative, to the system is positive. Coming to the internal energy, let me take internal energy of system increases gives del U positive. Internal of system decreases, del U is negative. Work work is done by system, del W gives positive. Work is done on the system, therefore del W gives negative. Let me write it clearly. Let me tell this. Find heat supplied to the if its internal energy increased by 60 joules. Here the internal energy states that del U increased by is 60 joules and the work done 20 joules. Del what we have to find, del Q is equals to del Q equals to del U plus del W according to the first law of thermodynamics. Okay, let me write clear. Therefore del Q we have to find from 1 we get del Q equals to 60 plus 20 is equals to 80. Coming to the next question. The internal energy change in the system is absorbed 2 kilocalories. Okay, observe 2 calories. Here units is 1 calorie is equals to 4.2 joules. Let me understand through a diagram like I'm shown that. Here the work done. Here the work done. Del W is 500 joules and the heat is 2 kilocalories. These are the gas molecules and this is the temperature thermometer. I have kept this. Okay, we know from first law del Q equals to del U plus del W. 2 kilocalories is equals to del U plus 500 joules. Since we have to find the del U from this, del U equals to kilocalories minus 500 joules. 2 into 4.2 into 1 kilojoules is 1000 minus 500 joules. 8.4 into 10 to the power of 3 minus 500 joules. 8400 minus 500 gives us 7900 joules is our answer, required answer. Moving back to the next question. 110 of heat is added to a gaseous system. The change in internal energy is del U is equals to 40 joules. What is the del W? Is the question we have to understand this. It was easy. From the first law, del Q equals to del U plus W. We know we have the question del Q equals to 110 joules equals to 40 joules plus del W. Del W is equals to 70 joules. Since it was work done by the gas, from I have told that in the sign conventions therefore the external work done equals to minus of work done by the gas. Since work done on the by the gas gives positive, since work done is positive, but the external work done is the negative of the gas, that is minus 70 joules. Answer. Okay, coming to the calorimeter. Let me take an container. I will take an Bunsen burner here. I want to heat this container. Del Q is equals to ms delta T. Therefore, S equals to del Q by m delta T. S gives us specific heat capacity. What is meant by specific heat capacity? For 1 gram 1 degree temperature increase, for 1 gram of solid or anything, how much temperature we have to increase for 1 degree Celsius temperature is known as specific heat. How much heat is required for the 1 gram to increase 1 degree temperature 1 degree Celsius of the temperature scale is known as specific heat capacity. Okay, coming back to the molar heat capacity, let me take an example of first law of thermodynamics. Del W and the gas molecules del Q. Del Q is equals to Nc delta T. C is nothing but molar heat capacity. Okay. Molar heat capacity always depends on the process itself. Let me clearly explain in the next slide. Molar specific heat of the, for example, we have to take water is 1 calorie per gram degree centigrade. For 1 gram we have to take, for 1 degree centigrade we get specific. For m grams we require 1 degree centigrade. Let me clearly write it. Is ms. M grams at delta T degree centigrade gives us ms delta T. Similarly to the molar heat capacity, for 1 mole how much degree centigrade we have to increase is known as molar heat capacity. For n mole 1 degree centigrade is Nc. For n mole at change in temperature gives us Nc delta T. Therefore, del Q equals to Nc delta T. Therefore S equals to specific heat del Q is equals to ms delta T. It will be more useful in the table which have discussed in that. Okay, coming to the thermodynamic process. What is meant by thermodynamic process? Thermodynamic process is the change of system from one thermodynamic state to another, from one thermodynamic state another is known as thermodynamic process. Basically, thermodynamic process is broadly divided into 5 types. Let us take this. Let me take in color of violet. Okay. Okay. Let me write it clearly. Isochoric isobaric process, isothermal process, adiabatic process, and last but not least, polytropic process. Let us discuss neatly in the next slides. Coming to the isochoric process. Isochoric process, we know that volume is constant. In a closed container, let me take an color and let me draw it. Gives us del Q, and these are the molecules itself. We know that del Q equals to heat supply to the system. Therefore, del U equals to a 10 moles NFRT by 2 is equals to, we know that FR by 2 gives C NCV del T. Let us derive this. Del Q equals to del U plus del W. Del Q is equals to NFRT by 2 plus work done. There is no work done. 0. Q equals to NCV into del T is equals to NFR delta T by 2. N delta T cut cut. Therefore, CV equals to FR by 2. CV is nothing but molar heat capacity at constant volume. Graphs of isochoric process. Let me take P versus V. V. Since volume is constant, we get a straight line here. Let me take pressure versus temperature graph. We get a straight line. Since PV equals to nRT, volume is constant, pressure is directly proportional to temperature, and the slope tan theta is equals to nr by P. Since volume is constant in isochoric process, let us take volume versus temperature graph. Since volume is constant, we get a graph like this. As technique. Given the graphs of What is meant by isobaric process? Simply in the states of matter we know this as Charles' law. In Charles' law we know that pressure is constant. Let us take an example like this. Let me take an container. Let me take an open vessel like this and then work done del W and then heat here and then gas molecules. Here we get del U. Therefore, del U equals to NFRT by 2 is equals to NCV into delta T. Del W is equals to integration of PdV gives, since pressure is constant, we get outside P into D. Therefore, del W equals to NR delta T. Since PV equals to nRT, pressure is constant. V equals to nRT. Therefore, del V equals to nR delta T. Therefore, we know from that first law of thermodynamics del U plus del W, first law, NCP into delta T is equals to NR delta T by 2 plus NFR, sorry, NR delta T, some at some work we get 2 N delta T will be cancelled both the sides. Therefore, CP is equals to FR by 2 plus R. CP equals to CV plus R. Molar heat capacity at constant press. Coming to the let me take pressure versus volume. We get in straight line. Pressure value versus temperature. Again we get a straight line. Let us take volume versus temperature. We get in straight line. Since PV equals to nRT, P is directly proportional to T. Therefore, V and T, we get an temperature like this, V1 and V2. Coming to the isothermal process, here temperature is constant, like boils. Let me take an. Hello?